Well, good evening. If any of you know the music group Pink Floyd, you'll also know the line, "Is there anybody out there?" Anyway, up to the subject matter. So I'm Roy Graham from DRC Computer. We have developed a range of applications. I'll talk more about that in a minute. Particularly, we're very focused on high-performance applications. So we take a number of FPGA-based boards. We've worked closely with Bitware, with Nalatech, with Alpha Data, and we program the applications onto those boards. So our sort of value, if you like, or our niche in the market is developing very high-performance applications. We've done a lot of work in many, many different applications areas. I'll talk about those as we go through the presentation. We're based in Silicon Valley, and we're actually a subsidiary of another California software company called Security First Corporation. I don't know how many of you are familiar with FPGAs, but we'll assume some knowledge, but not a lot. One of the ways to look at FPGAs from a high-level point of view is that you've got something like 10,000 processing units within the chip. So if you compare that, for example, with a CPU, where you might have 4, 8, 16 cores, the key is to find applications where you can get each of those 10,000 processing units executing in parallel. And in fact, all of those 10,000 do execute on every clock cycle. So the key is to look for that parallelism where you can take advantage of that technology. In many application areas, we're achieving 50 to 100 times acceleration compared to the equivalent software version. More often than not, we've taken, for example, a single-threaded, single-core application, software application, and when we go back to the basics, so you really look at the mathematics, if you like, behind the algorithms behind the application, and then you say, well, I'm now going to program this not for a single core or a single thread or even a multi-thread environment. I'm now going to program this for a device that has 10,000 processing units in it. So you go back to the fundamentals of the algorithm, and then you structure a solution around that structure. One of the big advantages of FPGAs is they're a very low power consumption device, typically around 25 watts. So if you kind of think about the math of this, let's say you're getting a 50 times acceleration compared to a CPU. You're replacing 50 CPUs with one FPGA. You're looking at 50 times 125 watts. So you're looking at 6 kilowatts and replacing that with a 25-watt device. So in environments where energy, space, real estate is important, infrastructure, then FPGAs offer a very good solution for that type of environment. One of the other advantages of FPGAs is they're highly secure. So the ability to get in and modify an FPGA once it's running is very, very difficult. It's nowhere near, it's a lot easier, for example, in software, to go in and provide a Trojan horse or hack into the software. It's virtually impossible to do that within an FPGA. So it also lends itself very nicely to secure-based environments. The other big advantage of FPGAs, because you've got this huge processing capacity, is you can start to look at things like analytics very differently. So rather than the conventional ETL structure where you store the data, you might convert it, and then you do the analytics on it on the back end, we can actually now do the analytics on the fly. So we can take in data directly into the FPGA, run the algorithms, the analytic algorithms that we want to on the FPGA, and then output the results. So it becomes a very real-time, responsive environment compared to conventional computer architectures. The sort of applications that lend themselves very well to FPGAs, if you're looking at how do I exploit this parallelism, are things like pattern identification, pattern matching. And for those of you who are very familiar with big data applications, you'll know that a lot of the analytics in big data is finding they call it the needle in the haystack problem. It's pattern identification, pattern matching types of applications. And in fact, people still talk about, well, we have this massive data source, we're going to find the needle in the haystack. I say that's the wrong problem. What you need to do is find the needle before you add the hay onto the haystack. So you do it as a streaming environment as you input the data. We joined the OpenPOWER Foundation in January. We actually had been working with IBM for a number of months during last year. And I've been very impressed and very grateful to the help and assistance we've got from both IBM, but also from other partners. And in fact, this conference has been very useful in terms of a lot of new introductions into other OpenPOWER members. So I've seen substantial value as a supplier in the OpenPOWER Foundation. All our solutions are cloud-enabled. The environments that we typically operate in often have dedicated data centers. We do a lot of work in the intelligence community. However, the applications have been architected and structured, so they're both highly scalable, but also it's possible to place those inside a cloud-based environment. And so if we take a look at just some of the applications that we worked on, you can see this. What I've tried to do here is contrast a cloud-based environment from on the x-axis to a dedicated environment, and on the y-axis from a server to a mobile. So many of the applications, again, because of the very low energy footprint, or low power consumption footprint, can actually be placed into a mobile environment, whether it's a laptop or whether it's a iPad-like device or even a cell phone environment. You'll see here that a lot of these applications have that ability to migrate from a dedicated server environment into either a cloud environment or into mobile devices. And in fact, frequently the applications operate like, we used to talk about client-server-based environments where there's a tight cooperation, if you like, between what happens on the mobile device versus what happens in the back-end server. So, for example, a biometrics application, fingerprint analysis might be a good one, where you might store on the local device the fingerprint set that's of known people that's local to that particular geography. But on the other hand, you may have travelers. So then you go to the back-end system as well. So you have this ability to migrate quickly between the mobile device and do the analytics on the mobile device, but also have access to the back-end cloud environment as well. So what I'd like to do, just sort of finish off the presentation, is talk about the two applications here that I've circled in red. One's the fuzzy search, and the other's the graph networking product. So on the graph side, we use graph networking, and we run two specific algorithms within this structure. So one's a Dijkstra. So Dijkstra looks for connections between entities. An entity could be a person, a location, could be a thing, could be an event, and then connecting the entities are things called edges. So you look for what are the tightness of the connection between the entities. And then you also look for what's called centrality. So you're looking for maybe specific locations, events, people that are central, if you like, to a structure. The environment that we run in, it's applicable to financial services as well as to the intelligence market and also transportation. So anything where you're looking for in real-time connections between things, between entities, it's an ideal application for that. Now, the big advantage of the FPGA, as I try to show here in the bottom right graphic, is that because of the evaluators, the things that run the Dijkstra and the between the centrality algorithms, those evaluators are small enough that we can actually get more than one of those, in fact, up to 100 of those inside an individual FPGA. So just think, you've got two sets of things going on here in terms of parallelism. So you've got not only the execution of those 10,000 processing units on every clock cycle, but you've also now got 100 instances of that particular algorithm running simultaneously inside the FPGA. Try and do that with a CPU. It's really hard. So that's part of the reason why we get the very high performance gain is through the use of large numbers of these evaluators inside the FPGA. So we're evaluating something like a million nodes and edge transactions within a second. So you can see that we can deal with extremely large and 100 million node, a billion edge networks. So this application was actually installed at a customer early part of last year. It was actually demonstrated at C15. We were there on the Xilinx booth. It was actually run on a Power 8 server, and we have it again here. So if you go to the Xilinx area of the OpenPOWER conference area, then you'll see this application being demonstrated. It's running on a POWER8 server, and we're actually using a Bitware Kintex 115 board to run this application. So the other application I'd like to talk about is the inline text and data analysis. So if you're looking at social media data, if you try and analyze that, people don't structure that in the way they might structure an email or you might see in a newspaper article. So they typically misspell, they use shorthand, they often use mixed languages when they're typing text or they're submitting something to Twitter or Facebook. So if you're analyzing that data, conventionally what you do in a more structured environment is you use a regular expression engine. So you'd say, okay, I'm looking for this particular expression and search through these documents for me until you find that particular expression. So it might be, for example, restaurants in San Jose is an expression you're looking for. In social media, and the only time it actually will raise a flag and say, okay, I found that particular string, is when it finds that exact match. It finds restaurants in San Jose mentioned explicitly inside the document. In social media, that doesn't work. I mean, people rarely spell things out exactly like that. So what you need is something where it's tolerant of the misspellings, the gaps, insertions, the mixed languages, for example, inside the message. So we have a fuzzy logic-based algorithm. It actually says, all right, well, tell me the string you're looking for, restaurants in San Jose, but also tell me what degree of tolerance you'll accept in terms of, for example, gaps, insertions, and deletions in that text string. And then when you reach a certain score, a certain an analysis level, then it'll raise a flag, and then you can actually go in and take a manual look at that particular message or that particular string or that particular document. So it runs through the product that we have installed is typically run at around 10 million characters a second through a single FPGA. And we're seeing around, we can load in up to about 1,000 simultaneous strings. So the other advantage of the FPGA is, whereas in a CPU you might be looking for one string at a time, as you do as you go through each execution of the application. In the case of the FPGA, you can search for 1,000 strings simultaneously. So you're literally streaming the raw data stream through the FPGA, and the FPGA's got the strings stored in it, and it'll look for these particular strings that you're looking for, score them, and then raise a flag when it reaches a particular threshold level. This application has the ability, like some of the others that I described on the previous slides, of actually being cloud-enabled. And so one of the clouds it could, for example, appear in is the IBM cloud. And the fact that it's already run on a POWER8 and it's already running within a Xilinx FPGA makes it ideally suitable for a cloud-based environment that supports an FPGA-based structure. So that's the last. I was only going to run through those two applications. If you've got any other questions, I'd be happy to answer those. Good. In which case, thank you. Thank you very much for your time.